points. All right, so they say, and I know it's kind of small to zoom in. I can zoom in here in a minute, but it says graph points A, B, D, E, and then label point C, the intersection of A, E, and B, D. Part B says find the slopes of A, E, and B, D, and then that should tell you then some type of relationship between the angles ACB and ECD. Then it says write equations for AE and BD. What are the coordinates of C? Now the coordinates of C, I'm going to go through and I'm going to show you how to do that algebraically, because here you could probably look at that and say, I'm going to count 1, 2, 3, 4, 5, negative 2, right? Not the way we want to do that, okay? Because what happens when they don't intersect at grid lines? How do we go through the algebra to solve that? So I'll show you that technique here in a little bit. And then it wants to use the distance formula. So some of you are saying the distance formula is what's throwing you off, right? Because they ask you to write simplified radicals. Okay, so we'll talk about how to do that here in a moment. And it becomes a very important practice for us to be able to simplify radicals because of what the rest of the year is going to entail. So the first thing says find the slopes of AE and BD. So I'm going to find the slope of AE first. So slope AE. And that's using -2, 4, and -8, -8. Okay, I like to stack my points. We talked about this before, so I can do that subtraction just a little bit easier. -2 minus -8. What's -2 minus -8? It is 6. Good. And I did that wrong, right? Top is y2 minus y1. Bottom is x2 minus x1. So -2 minus -8 should be on the bottom. And then the 4 minus -8 should give me what? 12. So 12 over 6 reduces to 2. Okay. Then we're going to do slope of BD. Okay, so slope of BD, B being -7, -1, and D being located -3, -3. So y2 minus y1, so we'll go -1 minus -3. And then we'll go -7 minus -3. What's -1 minus -3? 2. What's -7 minus -3? -4. What's that reduced to? -1/2. What is the relationship then between AE and BD, those line segments, if their slopes compare like that? They're perpendicular, okay? We've got opposite signed reciprocals here. So that means we've got perpendicular lines, AE and BD. So that's a right angle right there, okay? Now it says write equations for AE and BD. All right, so doing that, let's first, I'm going to rewrite this information up here. So we found the slope of AE to be 2 and the slope of BD to be -1/2. It then asks to find equations. And I asked you to watch that video or series of videos to refresh how to do this. But whenever you want to write an equation for a line, okay, the best way of doing it is to use this formula, y minus y1 equals m times x minus x1. And as you're going through this, that y is always going to be y, and that x is always going to be x. They don't change, okay? Only the things that have subscripts in the letter m are going to change, okay? But we talked about in that video that y1 and x1 are a point on your line that you're trying to find the equation for. So I'll find the equation of AE. So the equation of line AE. I need to use a point that is on that. Okay, so I've got a lot of options. Okay, if I look at AE over here, I look at that line. There are a lot of points on that, right? How many points are on that line? Infinite number of points, right? Okay, and if you choose any one of those, and let any one of those infinite points be x1, y1, and you use the slope that we found in the first part of 2, you will find the correct equation for that line. And it will be the exact same equation that your neighbor finds using different points on that line. Does that make sense? Okay. Now, that being said, even though there's an infinite number of points on there, some of those points are really bad points to choose. Because some of them, you don't really know what the accurate coordinates are. For instance, if I look at, just kind of zoom in here real quick. No, it's kind of fuzzy, but if I look at maybe that point right there, that's a bad point to choose, right? Because I have to guess. It's inside that box, right? Inside those 4 grid lines intersecting there. And I have to kind of guess on what its coordinates are. All right? Now, I'll get along when I guess and figure this out. I'll get a line that's somewhat comparable to AE, but it's probably not going to be exact. Okay? There are some other ones. Maybe that one's a little bit better to choose right there because it looks like it's at the intersection of grid lines, right? And then my ordered pairs are going to be integers, okay? Which is nice. That's what we're trying to look for, ordered pairs that are integers. Well, the best thing when they give me a segment is to use an endpoint that comes from that segment. Does that make sense? Because you know that A is exactly at -2, 4. You don't have to guess. Maybe it's at -2.1, 4.25. I'm not guessing. I know it's 100% at -2, 4. Or I could have chosen E, -8, -8. Does that make sense? Either one of those will get you the same result. So I'm gonna just kind of go through this both ways. Using A, let's use A. So A is the point -2, 4. So now I'm going to go Y minus Y1. So the Y1 is coming from the ordered pair. So I go Y minus 4 equals M being 2. Okay, and then X minus X1 being -2. So minus -2, what's minus a negative? Plus 2. And that's going to give me then Y equals, we can do it this way, be a little bit more explicit. Y minus 4 equals 2x plus 4, right? Can I add 4 and get Y equals 2x plus 8? And there's the equation of AE. So AE's equation, Y equals 2x plus 8. Okay? Now, like I said, you could have done this. Instead of using the point -2, 4, you could have used E, which was -8, -8, right? Okay. If I plug -8, -8 in, Y minus -8 equals 2 times X minus -8. And now let's evaluate that. That becomes Y plus 8 equals 2X plus 16, right? Subtract 8 from both sides, Y equals 2X plus 8. Is that the exact same equation? Use different ordered pairs, right? So the idea is if those two provide the exact same equation, then any ordered pair on that line is going to do the same thing. Okay? So AE is 2x plus 8. Now let's find the equation of BD. Okay? So I'm just going to use D. So B is located at -7, -1. So I'm going to write equation of BD is going to be Y minus Y1. Okay, so minus and negative becomes plus, right? Equals M. The slope of BD was -0.5. X minus -7 becomes plus 7, right? So I get Y plus 1 equals -1/2 X minus 7/2. I'm then going to subtract 1 from both sides, which is going to give me -1/2 X. Okay, subtracting 1 is the same thing as subtracting 2 over 2, right? So it becomes minus 9/2. And I'm going to write it as fractions. I'm going to change things to decimals because of what we're going to do next. It makes it so much easier to leave it as fractions. Okay? So that's how I find equations for those lines. Okay? Part Or the second part of C says, what are the coordinates of C? Some of you, like I said, are probably going to count, right? And I think on everybody's that would have probably worked. But let's see if I can get, if we count, we get 1, 2, 3, 4, 5, -5, -2, right? Let's see if we can reproduce that algebraically. Okay? We have two equations. One equation, AE, and the other equation, this one, which is for BD, right? Okay? Do those two lines intersect? And that's what they're providing C with, right? And you guys remember from last year that you graphically did this, and then you went through the work, and then the section called Systems of Equations to find the ordered pair that satisfies those two equations, okay? So every time you do a system of equations, you are dealing with two lines graphically that cross somewhere. And your solution to the system is the x and y coordinates of where those lines cross. So we've got a really nice way of being able to solve this. Are these both solved for y? So what's that tell us about 2x plus 8 and then -1/2 x minus 9/2? Substitution says that 2x plus 8 is going to equal -1/2 x minus 9/2. Right? Okay? If these two y's are the same, then these two things are the same. Now, this is why I left these as fractions, because it's really easy at this stage to get rid of them. Multiply everything by what? 2. So we get 4x plus 16 equals -x minus 9. Add x to both sides, so I get 5x. Okay. Subtract 16 from both sides, I get -25. What's that tell me x is? -5. Okay. Now, if I know x is -5, I'm going to plug back into one of these equations to find y. Which equation would be best suited to solve for y? Top one. Doesn't have any fractions, right? So I'm going to go y is equal to 2 times my -5 plus 8. That's -10 plus 8, right? It's me -2. So x was -5. Y was -2. Is that the ordered pair that we see graphically when we count over and down, right? Okay, that's how you need to do that algebraically, and this is 100% very similar to questions that you're going to see on the Intercourse exam, where they need you to show the work. Okay. All right, so we're good there, right? Now the reason I need that is because the next question is find A, B, B, C, D, C, and D, E, right? If I'm going to find those distances, I need that ordered pair that goes with C. All right, so I'm just going to kind of clean things up here. We want to find distance. Remember, C was located at -5, -2. We want to find distance, and if you remember, distance, we've talked as this. Okay, and sometimes you might see distance written this way. I don't know how the end of course exams reference sheet that they give you is going to look. I don't know how the ACT reference sheet might have changed since the last time I looked at it. But when we do difference in x's, a lot of times they might write that as that, and they'll say delta x squared, and then they'll write delta y squared. Does that make sense? Okay. And delta just means change, okay? And change algebraically means do subtraction, okay? So those two things are saying, those two formulas are saying the exact same thing. So let's find the distance of AB, okay? So AB is going to use, A was -2, 4, and B is -7, -1. So I subtract the x's. -2 minus -7 is what? -5, or sorry. Yeah, +5, right? Does it matter whether it's positive or negative though? No. Square that, you get 25. And now I'm going to go 4 minus -1. 4 minus -1 is 5. Square that, you get 25. So now, what we've been doing so far in class is said that this is radical 50 and leave it as radical 50, right? And I'm going to. Right now, I'm going to leave it as radical 50 because my goal is to make an argument about the triangle here in a moment. Okay, once we find all these distances. But then we'll go back and we'll simplify these because I think that's maybe where we were seeing issues in the homework. So I'll talk about how we simplify those all at the end. The next thing is to find what, BC? Okay, so C is located at -5, -2. So -7 minus -5 gives me -2, right? Square that, you get 4. -1 minus -2 gives me 1. Square that, you get 1, right? Okay, so that distance is radical 5. Is that doable? Okay. And hopefully that makes some sense to us. If we look over here at this distance, B to C, pretty small, right? Radical 4 would be 2. Okay, so if we compare maybe that distance there to that one, because this one's got a slope, it's going to be a little bit longer than this one, right? And radical 5 is a little bit longer than 2. So that makes sense. Next one is DC. So point D is at -3, -3. So subtract my x's. -5 minus -3 gives you 4. After I square it, right? -5 minus -3 gives me 2. Square that gives me 4. -2 minus -3 gives me 1, right? Square that, you get 1. So there I get radical 5. Okay. And the last one is DE, right? And E was located at -8, -8. -3 minus -8 becomes 5. Square that, 25. -3 minus -8 again should give me the same result. And that gives me a radical 50, correct? So let's think about what we've just done here. We first identified that we had a right angle there and a right angle there, right? Are those two angles congruent? We just now found that BC is congruent to CD, right? And we also shown that AB is congruent to DE, correct? Well, that tells us about those two triangles. They are congruent by what theorem? HL. Hypotenuse leg tells us those two triangles are congruent. Okay. Now, when we go into Math Excel and I want to type in radical 50, it may tell me that we need to simplify that, right? Okay. So radical 50. Okay. A couple different approaches here, but every single approach is trying to provide a way for you to determine what is the largest perfect square that divides 50. Okay? So think about, and when it divides it, when I say divides, there's kind of an understood that statement that our quotient that we get is going to be a whole number. Okay? Yeah. Yes. Okay. So you can, what she said is, you're talking about the factor tree. Yes, that's what I'm talking about. We're going to do prime factorization. But my hope is when we do prime factorization, that's an algorithm, it's a step-by-step process that is always going to find that largest perfect square that divides 50 for you. Okay? What I do, I'm not saying this is right, but it's a lot more efficient, is I know that when I want to divide 50 by a number, and I want to get a whole number, is that the smallest whole number I could get back would be 2. Okay? So, if I look at 50, and really any number, if I look at the radicand, basically to get a integer back, I need to divide it by something that is smaller than half of that radicand. Does that make sense? If I divide 50 by 40, am I going to get a number like 2 back? No, I'm going to get a number between 0 and 1, right? I need to get at least 2 back, okay? So I'm going to take 50 and look at that radicand, divide it by 2, and it gives me 25, right? So I'm going to start trying to divide 50 by perfect squares that are less than 25. The perfect squares that are less than 25 are, or less than or equal to, are 4, 9, 16, and 25, right? Those are the only numbers I have to check to see if they divide 50 evenly. Which one does that? 25, right? So what is this? What we do here is we make the argument that radical 50 is the same thing as 25 times 2 underneath the radical, right? Now, it's because of law of exponents. This is a situation that you've been taught this process, but you don't necessarily have the math under your belt to really understand why this works. But when I have a product of radicals, we can actually do this. We can put them in their own radicals. Okay? And what does that make radical 25? 5. And we get 5 radical 2. Okay? Now, you've probably been taught the factor tree. Okay? We call it the prime factorization of 50. And what it means is that I'm going to take 50 and start dividing it by something that I know divides it. Maybe you know 2 divides it. Maybe you know 5 divides it. Maybe you know 10 divides it, right? Okay? Maybe I go 5. And then over here I'm going to go 10. That divides 50, right? Now the idea is what we've just done is kind of like what we did here. We now know 50 is equivalent to radical 5 times radical 10. Does that make sense? Okay? But radical 10 will break down a little bit further. Radical 10 is the same thing as radical 2 times radical 5, right? Okay? So what happens then is that we call this the prime factorization because all of these numbers are prime. 2, 5, and 5 are prime numbers. And we stop at that point because if we kept going, 2 goes to 1 and 2, right? 2 goes to 1 and 2, right? 2 goes to 1 and 2, right? And would I ever stop? No. So you stop at prime numbers, okay? Which just tells me that radical 50 is the same thing as radical 5 times radical 5 times radical 2, right? Okay. Now you guys know that when I multiply two numbers together, say I take, don't even worry about the radical, say I take 5 times 5. How can you rewrite that using exponents? 5 squared, right? Well, now I've got radical 5 times radical 5. So can't I rewrite that as radical 5 squared and then times radical 2? Well, what's a square root and a power of 2 always do to one another? Cancel each other out, right? They're called, maybe canceling out is not the best word to use, but they're called inverse operations. They undo one another, okay? So what it means, if I start with 5, take the square root of it, and then square that result, I should get back to 5, okay? Call it inverses. Let me show you what I'm talking about here. If I take the square root of 5, where's my square root key? Is that the square root key right there? Okay. If I take the square root of 5, hit enter, I get that number, and now square that, I get back to where I started, right? So they undo each other. So the thing we do is we just cross these out and say, you know, you use the terminology they cancel, but then all you're left with is 5 radical 2, right? When you guys were in algebra 1, you're probably taught find the groups of 2's, right? The groups of factors that are pairs. So you say there and there pair up, right? And then they taught you, well, just take the number and put it out front. And then the things that don't have a pair go underneath. The reason that works, the reason you do that, is because of this concept that we wrote in blue. Does that make sense? Okay. I think that's a long process that as much work with radicals that we're going to do in the coming weeks and months. Every time you see a radical and you go through that process, you're going to waste a lot of time. And I think it's the best thing to do is to kind of look at that radicand and think about half of it. And now what perfect squares that are less than that, we'll divide it evenly. Okay? Think about this. If I take radical 42, okay, what's half that? What's half 42? 21, okay? So the numbers that are less than 21 that are perfect squares are 1, 4, 9, 16, And that's it, right? Okay. Does 4 divide 42 evenly? Nope. Does 9 divide 42 evenly? Does 16 divide 42 evenly? Nope. So what's that telling me about radical 42? It's already simplified. Okay. We don't try 1 because it's trivial. I just get back 42, right? Okay. So that's kind of the process that we go through when we're trying to simplify our radical. Okay, we can do that. So you got a particular distance to be radical 90 over 4, right? Okay. What I think is important for us to understand is, multiplication and division are very intricately associated with one another, right? They're very intertwined and very similar to one another. So a lot of the rules that we use for multiplication of radicals exist with division as well. And what I mean by that is if I had radical 50, okay, we can rewrite that as radical 5 times radical 10, right? Or if I started with radical 5 times radical 10, I can rewrite that as radical 5 times radical 10 that way, right? So I can kind of split these things up the way I want to within the radicals, okay? Or I can split them up and provide them their own radicals. And that's kind of what we want to do here. When I have a fraction and the entire fraction is underneath the radical, we want to write 90 in its own radical, and we want to write 4 in its own radical. Okay? And the whole reason of doing that has to do with your law of exponents. Okay? When we have a little bit more time, I'll go into greater detail on those laws of exponents and how that operation works. But now, it's just 2 problems like we just did together in the same problem. Does that make sense? So I'm going to simplify 90, radical 90, and then I'm going to simplify 40. Okay? When I look at radical 90, we could do that process where we do the prime factorization, do that little tree thing. We could take half of 90 and recognize that 45 is half of 90, so I start trying to divide by perfect squares that are less than 45. But when you see 90, because this happens a lot with particular values, isn't there a perfect square that kind of jumps off the page at you that divides 90? What perfect square do you know will divide 90? 9, right? Okay. So let's write this as square root of 9 times the square root of 10. The reason I would do that is because now if I take 10 and I think about half of 10, which would be 5, I only got to try one perfect square that's less than 5 to see if it divides 5 evenly. And we know 4 does not do that, right? So it just makes that process of checking perfect squares a little bit easier. What is radical 9? 3. 3 radical 10. Okay. Now on the bottom, what's the square root of 4? 2. So I get that. Okay. 3 radical 10 all over 2. And that's my final answer for that distance. If you guys want to check to make sure that you've simplified a radical correctly, all you have to do is take the number on the outside, square it. What do I get if I square that? 9. And now multiply it by the number that's left on the inside. What's 9 times 10? 90. And that gets you back to what you started with, right? Okay. And that's hopefully kind of reiterating the idea that we're trying to divide out the largest perfect square. And when I square 3 and I get that 9, that's proof that that was the number that was the largest perfect square that divided out of 90. The reason we do that, the reason we simplify radicals is because in further calculations, it's going to be much easier to deal with, even though it's an uglier looking expression, 3 radical 10 over 2, it's going to be a lot easier to do other algebra with that than in comparison to dealing with radical 90 over 4. Okay? The same concept of, why do I change 2/4 to 1/2? Because if I want to multiply 2/4 by 10, it's a lot easier to multiply 1/2 by 10. Okay? So simplifying and reducing things is meant to alleviate further calculations, make them a little bit easier. We want to leave it this way too, okay? And I know MathXL is going to tell you at times, type your radical in to 2 decimal places or 3 decimal places or whatever, okay? But there's also going to be points in time where we want the exact answer, okay? And it always blows people's minds in this class when I start jumping back and forth between exact answers and rounded answers, okay? And we'll do that here pretty soon. My suggestion to you, okay, is to always, regardless of what they're asking you for, in any math class, any science class that you ever take, learn the techniques and learn the work involved in finding the exact answer. And every time you do a problem, first find the exact answer. And then it's really easy to convert that to whatever decimal you need to, like just typing the exact answer in your calculator. Does that make sense? Okay. In addition to that, when we start working with radicals a little bit more heavily than what we currently are, we're going to have to learn how the calculator actually works, because we can type things in thinking it's the way we wrote it by hand, and our calculator doesn't do the order of operations the way we think it should. Okay? So my idea is don't rely on the calculator too much. Find the exact answer. It's going to be a much better, more preferred result anyways. Okay? Which kind of, I think,